Have you ever taken a video of, I don't know, a busy street or maybe your dog playing in the park and just wished you could freeze time and walk around inside that moment? Well, for years, AI has been getting pretty amazing at turning photos into 3D spaces. But there's always been this one giant catch: motion. The second anything moves, the whole 3D world just kind of falls apart. But a new paper might have just cracked the code by teaching AI to see the world less like a static photograph and more like a stage play. Let's dive in and see how they did it.
Okay, so this right here, this is the whole problem in a nutshell. On the left, you've got a 3D reconstruction of a room that's perfectly still, it's clean, it makes sense, it looks great. Now look at the right. That's what happens when you try the exact same thing but with a person moving around. It is a distorted, glitchy disaster. I mean, the best models we have, the ones that are absolute geniuses with still life, they just become completely useless in the real, moving world.
You know, a good way to think about it is like when you take a panoramic photo on your phone. If you hold everything perfectly still, it's beautiful, right? But what happens if someone walks through the shot? You get that weird, stretched out, ghost-like person. Now, just imagine that exact same glitch, but happening in 3 dimensions with every single frame of a video. Yeah, that's the massive challenge we're talking about.
So that leads us to the million-dollar question. Why is this so incredibly hard for AI? Why does just a little bit of movement cause the entire 3D model to have, a total digital meltdown? Understanding this is really the key to appreciating just how clever this new solution actually is.
It all comes down to this one core idea called the rigidity assumption. See, older state-of-the-art models, like a really good one called DUSt3R, were all built on this very simple but flawed belief that the entire scene is one solid rigid object. It basically assumes the only thing moving is the camera. And that's fine for buildings or landscapes, but in the real world, well, people walk, cars drive, things move. Every single one of those movements completely breaks that fundamental assumption.
So the moment that rigidity assumption shatters, the AI gets totally and utterly confused. It's like it's trying to solve a puzzle, but some of the pieces are actively getting up and running away. It just can't figure out what's supposed to be the background and what's moving all on its own.
And hey, don't just take my word for it. The researchers behind this new solution, they put it perfectly. They said that object motion disrupts the camera pose-based alignment. So, in simple terms, that means the AI can't tell if a dot in the picture moved because the camera moved or because the object itself moved. And that confusion leads to it connecting the wrong dots and making just plain wrong guesses about how far away things are.
So how in the world do you fix a problem that big? Well, a team of researchers from KIST AI, Sony AI, and ETH Zurich came up with a brilliantly simple idea in their paper, Dynamic, Dense, Unconstrained Stereo 3D Reconstruction, or as they call it, DUSt3R. Their big insight, their aha moment, was to just stop treating the world like one solid block. Instead, they decided to treat it like a stage play. Right? You've got the background scenery, the stage, that doesn't move. And then you have the actors who are all moving around independently. What if you could just teach the AI to see the world that way?
And that is exactly what they did. Their method, DUSt3R, follows 3 pretty straightforward steps. First, it looks at the scene and identifies everything that's moving, and it creates what's called a dynamic mask to basically put a box around it. Step 2, it reconstructs the static background, all the stuff that's not moving, using the old reliable camera pose method. And then for step 3, it tracks those moving objects completely separately, using their own unique motion data. It gets that data from something called optical flow, which is basically the AI's best guess for how every pixel is moving from one frame to the next.
And this is a perfect illustration of that very first step. On the left, you see a frame from a video of a duck. Pretty simple. But on the right, look at that. That's the dynamic mask the AI generated. It has perfectly isolated the moving duck from the static background. It now knows there are 2 different things to track, and they each need their own set of rules.
It's a fantastic idea in theory, right? But the real question is, does it actually work in practice? Well, the researchers put it to the test, and honestly, the results are kind of stunning.
Okay, so this slide shows a really key concept called correspondence. All that means is the AI is trying to draw a line connecting the exact same point on an object as it moves between frames. On the left, you see an older model trying to track a moving dragon. The lines are just a chaotic mess, it has no idea what's going on. But now look at the right. D2S3's lines are clean, they're precise, they perfectly follow the dragon's motion. The AI knows exactly where every single point has moved.
And that super accurate tracking leads directly to this: way better depth maps. A depth map just shows how near or far every pixel is. On the left, that's the result from another leading model called DUSt3R, which was also designed to handle motion. It's okay, but it's blurry and kind of undefined. Now look at the right. That's DUSt3R. Just look at how crisp and clean the outlines of the person and the dragon are. The model has such a better understanding of the 3D space.
And the numbers absolutely back it up. This table shows something called endpoint error when tracking moving objects. It's basically a score for how wrong the model is, so lower is better. The original DUSt3R had an error of over 35. DUSt3R, the other dynamic model, was even higher, almost 42. But DUSt3R, it slashes that error all the way down to 25.31. I mean, that's not just a small improvement, that is a massive leap forward in accuracy.
So what does all this improved accuracy really mean? I mean, this isn't just some academic exercise. This kind of breakthrough has huge implications for the future of how we interact with technology and maybe even how we interact with our own memories.
Being able to accurately map a dynamic, moving world unlocks so many crazy possibilities. I mean, think about augmented reality, where digital things can actually realistically interact with people moving around your living room. Or think about robots that can navigate a chaotic, busy warehouse. We could even generate those incredible bullet time special effects, like from The Matrix. But get this, from a single, normal video camera.
And here is the proof. This incredible shot was not made with 100 different cameras. No. This was generated by DUSt3R TS3, taking a bunch of frames from a single video of a moving car and stitching them all together into one coherent 3D scene. You can literally see the car frozen at multiple points in its turn, all existing in the same 3D space. This was basically science fiction before now.
Okay, now let's be fair and balanced here. The enthusiast in me sees a total game changer that sets a new bar for performance. But we also have to listen to the skeptic. And the paper's authors are really clear about the limitations. First, DUSt3R's performance is completely dependent on a totally separate AI model to calculate that initial optical flow, that guess about how things are moving. If that first model gets it wrong, DUSt3R will be wrong too. Second, it currently only processes 2 frames at a time. So to create a truly seamless walkable 3D video, this method still needs more work. It's a huge step forward for sure, but it's not the final step.
So after all of that, what are the most important things to remember from this incredible paper? Let's just boil it all down into 3 key takeaways.
First, the big problem. Traditional 3D models totally fail when things move, because they assume the whole world is a single rigid block. Second, the clever solution. DUSt3R ditches that idea and treats scenes like a stage play, separating the static background from the moving actors. And third, the big payoff. This simple change in perspective massively improves accuracy, unlocking a future with hyper-realistic AR, way smarter robots, and some mind-blowing new visual effects.
Ultimately, this technology is about more than just data and pixels. It's about capturing life as it actually happens, motion and all. Which kind of leads me to a final question for you. If you could use this tech to perfectly freeze and explore any single moment from your past, what memory would you choose to preserve forever?